So recall, in the previous video, we were looking at the trig functions as ratios from a right triangle. So we previously looked at the trig functions as ratios from a right triangle. Where we had adjacent next to our angle theta, opposite, and then the hypotenuse. And we also had the relationship between adjacent, opposite, and hypotenuse. So, and by the Pythagorean theorem, we had the hypotenuse squared was equal to the adjacent squared plus the opposite squared. So the trick is to find the appropriate right triangle to match the square root that we are looking for. So our square roots, again, are a square root of something squared plus or minus something squared. So for the first square root we're looking at a square root of a squared minus x squared. If that square root a squared minus x squared pops up within our integral or within our integrand, then anytime we have subtraction, the first things come, the thing in front of the subtraction comes from our hypotenuse. So we're going to set our hypotenuse equal to a. And then the thing being subtracted off will be one of the legs. And the square root is the remaining leg. So one leg will be x, and the entire square root will be the other leg. So if we go to set up our right triangle, we have our angle theta. We know the hypotenuse here will be a. Again, Pythagorean theorem. If we have a subtraction inside our square root, that means that we've done hypotenuse squared minus either adjacent squared or opposite squared. So that a is our hypotenuse. We are going to go ahead and just let x be our opposite. And we'll take the square root of a squared minus x squared to be our adjacent. So what we get from here then is that we have sine of theta is x over a, or in other words, x is a times sine of theta. And we can easily, for substitution, we also need a dx. We can easily get dx from there. We get that dx is equivalent to a cosine of theta. So this is going to be extremely useful. We have an x equaling a sine theta, and we have a dx equaling a cosine theta. Oops, I forgot my d theta. A cosine theta, d theta. We also, though, have another relationship. So a simple relationship involving square root a squared minus x squared. If we don't want to involve our x as well, we have that cosine of theta is equal to the square root of a squared minus x squared, that whole square root divided by a. So this means then that we have our square root a squared minus x squared as just a cosine theta. So having drawn this right triangle, if our integrand involves square a squared minus x squared, we can replace that square root with just an a cosine theta. We can replace any other x's with a sine theta, and we can replace dx with a cosine theta d theta. For integrals involving a square root x squared plus a squared, so if there's a square root x squared plus a squared inside the integrand, the plus means that we have our two legs here. So x will be one leg, a will be our other leg, and then we also have the square root x squared plus a squared will be the hypotenuse. If there's addition inside that, solving for the hypotenuse. So in this case, the triangle that we want to work with, we have square root x squared plus a squared as our hypotenuse. Then from there, we will also put x on the far side and an a as our adjacent. Reason for this will allow us to now work with tangent and secant. If we swapped the x and the a, we would instead work with cotangent and cosecant, which is perfectly fine, but we are more used to working with tangent and secant. So from this triangle, our relationship involving just the x and the a will be tangent. So we have tangent of theta is x over a, or x is equal to a tangent of theta. If we solve for dx, we get that dx is equal to a secant squared theta d theta. So here we have an x and a dx solved for. Neither of those use the square root. We might as well go ahead and also figure out our relationship involving the square root. So involving that square root and the a, that's our hypotenuse and our adjacent. So let's go ahead and do secant of theta is the hypotenuse, square root x squared plus a squared over adjacent, so over a. And that becomes square root of x squared plus a squared is equal to a secant theta. So again, we now have a substitution in place of our x. We have a substitution in place of our square root x squared plus a squared, and we have a substitution in place of dx. For our last case, we're looking at the square root of x squared minus a squared. This time around, since the x squared is before subtraction, that x is acting as our hypotenuse. So we have our hypotenuse is acting as x. We have one leg is a, and the other leg will be the square root of x squared minus a squared. So for this triangle, again, This time around, x goes as our hypotenuse. Again, we get to pick between our two legs. Once again, so we can work with tangent and secant instead of cotangent and cosecant. I'm going to put the a as my adjacent, and the square root x squared minus a squared will be my opposite. If we go ahead and do the x first, the relationship that involves both that x and that a, you could either use cosine or secant. Let's go ahead and do secant of theta is x over a. That means that x is equal to a secant of theta. And that leaves us with dx is equal to a secant theta tan theta d theta. So here we have a relationship again between x and theta, and we know our substitution for dx as well. Furthermore, that square root x squared minus a squared, the simplest relationship for that one is our tangent. So we have tangent of theta is equal to the square root of x squared minus a squared, whole thing over a, or square root of x squared minus a squared is equal to a tan theta. So I typically just redraw the right triangle every time, so I don't have to memorize these formulas, but you should know which right triangle applies. As a general rule of thumb, when we go to draw our right triangles, A should always be either the hypotenuse or the adjacent. If A is the hypotenuse, we want the simplest thing we can on opposite, so we put x. If the A is not the hypotenuse, then the other leg is just automatically determined because we picked A as adjacent. So in both our second two cases, A was adjacent, which automatically determined the opposite side. So in the next videos, we will go ahead and do some examples where we actually run through and do some substitutions with Trig.